Second half. I'm going to some of the stuff I left on yesterday about transistors, ratios, clock drivers, loads, timing, etc., and relate that to a design that I did, which I'll go into in more detail in about 30 minutes. Okay, first of all, let's talk about this pull-up device a little bit. Here I've drawn the essence of a load device. I omitted the yellow implant. It's not particularly relevant to this picture, but be careful. A lot of people tend to forget that, and your design won't work if you make all your pull-ups regular transistors. It's fairly obvious how to measure the geometric impedance ratio on this device. That is the length-width ratio, or the Z. The length over width. It's the number of squares long that the channel is. On one of the pages I handed out, there are some process parameters where the channel of a turned-on device is treated much like any other layer. That is, it has a resistance in ohms per square. And in this case, for example, it might be 4 squares. That would be called a Z equals 4 pull-up device. That one's fairly simple, and in fact, if you make the connection from the gate to the source by a budding contact off on the side, you don't have any problem on how to measure that. But quite often, for compactness of design, we put a budding contact right on the edge, right here. And that's done by putting a 2 lambda by 2 lambda cut here and here, making a 2 lambda by 4 lambda cut, often drawn in black. And we put metal, of course, over that, surrounding it. But it's also necessary to make a good, valid contact to extend the diffusion layer, essentially in a square around the lower half of that contact. This complicates the measurement of this device somewhat, because now if you look at the active channel area, that is the area where the red and green overlap, it includes this region on the end, which has been flared out. Okay, now the channel is no longer a rectangle, and it's no longer obvious how to measure its length-width ratio. If you measure it this way all the way to the end of the wide part, you'll be approximately right. But in fact, since this end is a little bit wider, this thing will have slightly less impedance than you calculate, which means the ratio of your inverter, the K of your inverter, might be a little bit low. That's probably not the direction you want your errors to go, because if your ratios are a little bit low, you stand a chance of that inverter not producing good solid logic levels. If you let the ratio get a little bit high, the only thing that can happen to you is it gets a little bit slower. So to be conservative, you should measure the length only down to the point where the green area gets wider.
What's a little bit?
Well, the difference in these measurements will give you an idea of what the difference in K might be between that conservative way of measuring it, which makes the effective K bigger than your estimate, and the unconservative way, which makes the effective K a little bit lower than your estimate. So you can bracket your errors that way. You can measure it halfway in between if you like. But to be conservative, I always measure it to here. So if you want 4 squares, make it 4 squares from here to here, and then another lambda to take care of that wide area. This form of a pull-up device has several advantages. It's very compact. The width here, including the buried contact, is pretty compact compared to one where the budding contact, I didn't mean to say buried contact, the budding contact here is small compared to one with it out on the side. In either case, this kind of a pull-up device has the advantage that this is always the output node of a gate. This output is available in all 3 colors. There's blue because you have to have blue to make a contact. There's green because that's what the lower switch network is made of, and that comes into it. And then there's red because the gate of the pull-up device, which is part of that node, is red. If you make your gate with a buried contact here instead of a budding contact, you sacrifice the ability to take the output on the metal layer. So that's a possible drawback to using a buried contact there. There's a few questions. Let me take them now. Rick?
In NSIL 2, Dick, if you're using the oversized contact holes that are rid of this uncertainty that
Ah,
you're talking about?
it's an interesting point. I don't think I ought to talk about that right now because I don't know enough about it, but there's some possibility you can do without this extra green overlap in some processes. That's what Rick's mentioning. Jeff?
Yeah. I'm a little confused about the contact cuts. When the masks, there are actually two different cut processes, and so when the masks are generated, it's done by an ANDing of what's on the drawing.
There's in
Generate
fact
two
only
different-
one cut mask, and it corresponds to these areas with the black X's. And that cut can contact either the diffusion layer or the poly layer. If this cut is over both layers, the poly's on top, and the cut stops when it gets to the poly. And there is in fact still, underneath the poly, there is still some thin gate oxide, and there's in fact some active region underneath the cut. So the cut goes down and contacts either the poly or the diffusion. In Icarus, if you look at a layout in
It's the
Icarus,
thin oxide layer that stops it.
right, no, it's the silicon that stops it. The polysilicon stops the cut. It cuts through oxide, stops the silicon. In Icarus, the stipple patterns that we use for the different layers are very carefully chosen so that when you make a contact correctly, you get a certain pattern of a dark area with white dots in it. And the white dot pattern is different whether it's contacting green or red, and it doesn't matter whether there's green underneath a red, and therefore you can unambiguously tell by eye whether you're contacting the green layer or the red layer. And if you leave out any layer in a contact, it looks different, and you can learn to recognize bad contacts. Will?
If I want to take off a green line to the right, both from the top to the bottom, how close can I come?
The rule says to take a green line off this way, you should leave 1 lambda separation between it and this red. In fact, some outlines come out, some layouts come out with it right there, but that's, in my interpretation of the design rules, that's a violation. You could probably get away with it. If you want to come off the top, it's the same rule, 1 lambda separation. Ken?
The other question is, the opposite question, if you want to come out in red, can you just start right there at the bottom right-hand corner in red, if you will, and go to the right?
Yeah, you can come out in red anywhere. You can come out here, you can come out here, wherever. You can go both ways.
Okay. I still don't understand, whenever these contacts have been drawn, where the red and green overlap, there's a darker area, which you sort of put in green.
This, right.
No, not that one, it's the long, thin one. That
This one here.
represents the overlap, I guess,
Right.
between the red area and the green area.
Right, and that's part of the transistor channel because it's an overlap of red and green. As the channel comes down and gets wider just before it comes out the end.
Okay, and you get thin oxide into that.
There is thin oxide, right?
It's the thin oxide that's in that overlap region that's important.
Yeah. Dan.
I missed the point about when we lay these things out, we don't do any, we don't try to establish any thin overlap. I mean, that just happens, right? Because of the way it cuts.
In the layout, you actually do have this overlap. You have a green flash here.
Right?
1 lambda, it's 4 lambda square. 1 lambda of it is underneath the red gate area. You actually draw that overlap. It's hard to see with the metal over that and all the layers present. It's hard to distinguish that as a separate region. But in fact, if you draw it big enough and look carefully, you can see it. And if you disappear the metal layer, you can see it more clearly. Okay? Another question? Bill?
Yeah, I was just going to say, when the thing gets made, that area that you drew in there doesn't really exist. There's no diffusion there.
There's no
Around
diffusion.
the edge of it, a transistor occurs, and that's what you're accommodating.
Well,
with your-
what I'm saying is the diffusion doesn't get under there because there's poly, but it does make a thin oxide region, which is part of the channel of that transistor. And I tend to ignore it because it's hard to say geometrically how to account for it.
Most people that do take it into account cut it in half, and that's a pretty accurate.
Ah, okay, so you measure it halfway between these. Severo?
Can you not just enlarge your metal down by a lambda and get rid of this whole problem?
Yeah, you can, if you make the metal 1 lambda longer and pull the green flash down and lengthen your cut a little bit so they don't overlap, that gets rid of that problem almost. It makes it more obvious how to measure it. But that still has a disadvantage, which I was about to mention for this one, which is that The effective K, or the effective length-width ratio of this transistor, depends, unfortunately, on variations in the alignment or slight misalignments. If you shift this red gate up and down, you're shifting sort of a narrow channel region out one end here and a wide region in the other end. And so the K is, in fact, alignment dependent. And that's sort of a problem. That means the speed of your devices will be more dependent on where they came from on the wafer and how good the operator was feeling that day, things like that. Whereas if you make it with a contact cleanly separated by at least a separation of lambda so that you never get a wide region under there, then it'll be alignment independent. There's one less variation you'll have to worry with. But the compactness of this is generally worth those kinds of variations.
You're saying that to be super conservative, you would make the cut through a little longer so you would never have that change so the green areas will occur.
Yeah, there's various ways of being super conservative and making sure that you keep plenty of clearance around both ends of this thing. Ron?
As you slide the red area up and down, what you're doing is sliding, you're just cutting off where that fat green area on the bottom butts up against it. But that fat green area more of it doesn't slide underneath the red area because it's prevented from diffusing into that area.
Yeah, but I'm not saying that sliding the red is causing more diffusion to be under it. I'm saying that it causes more channel, more thin oxide area. The green, in fact, we call it diffusion. It really defines the thin oxide mask. And what I said is true. As you slide the red, the shape, the amount of wide area in the channel does in fact change, and the effective ratio then changes a little bit. On long pull-up devices, that effect is going to be very small. If you made a short pull-up device where the gate was really only 1 or 2 squares long, that effect could be very large, and you wouldn't build it this way. Okay, any other questions on that? Okay. Let's see what's next. We go back to this picture I drew yesterday, which is a super buffer. That is a depletion load which is driven with an active signal to make it an active pull-up device, and a enhancement pull-down device just like in an ordinary inverter. How do you go about estimating the speed of this device? We talked about the rise time of a signal out here on the load. But to get the effective speed through a super buffer, which typically has 2 inverters associated with it and possibly a clock control line input, possibly some other signal being ORed in with it so that it can gate a clock. To calculate the speed of it, you have to look carefully at the rise and fall times of every node. And you have to add up the times, such as the rise time here plus whichever is greater, the end of the rising signal here or the end of the falling signal here, in order to find out what the effective low to high transition time is. And for each direction that you're interested in evaluating out here, up or down, you have to look at 2 possible signals, draw the timing and see what their delays are, find out which one is the limiting case, and take that as sort of a worst case estimate of what the prop delay through that is. And since this can be hooked up either way, in either inverting or non-inverting form, there's really 4 different cases you have to analyze in general if you want to understand that thing. And I don't have any tabulation of those results, but they're simple to do, and I think you ought to. I will go through one example here in a moment. One of the big issues in designing these circuits, as we've mentioned before, is how you go about driving these big loads. And putting a super buffer on here is great. It's a good thing, and it picks up a factor of 4 in the rise time on that node, but it doesn't answer the whole question. For example, if the signal that you're coming in with here is from a device that's fairly small, say it has a minimum size pull down with a gate capacitance of about 1/100th of a picofarad, and what you're trying to drive over here is the outside world with 5 TTL loads and 50 picofarads. And you've got a factor of 5,000 in gain, I believe, if I estimated that right. Gain of essentially the amount of charge you're using to make that voltage swing. So I'm not talking about voltage gain, but it's sort of charge gain or current gain. And how do you get that? You can obviously get it from any device. Any single inverter is capable of driving any arbitrary load if you wait long enough. But you don't want to wait that long. So the question is, how do you optimize the time it takes to make that voltage transition on this big capacitance, given that you only have a puny amount of charge, a puny driver device out here to make it happen? So let's look at that sort of in the abstract. Let me erase this picture and start over. In the general case, in any technology, you have an inverter. Say this is a standard minimum size inverter. Make this a one-to-one device, and this may be a K equals 8, so it's a Z equals 8 pull-up. Okay, this will be sort of the minimum standard device, and from the output of this dude, we want to get out to driving 50 picofarads maybe. So the way you do that, symbolically, you can think of just drawing bigger and bigger inverters on here. Okay? Each one of these hopefully gives you some amplification. This brings up another degree of freedom in inverters that we haven't discussed a lot. We've mentioned it a little bit. And that is that every inverter is characterized by two numbers. It's, in the simplest case, it's characterized by a K, the effective impedance ratio of its pull-up to its pull-down, and also by some absolute size. In this case, pick the size of the driver device, or to make things simpler, pick the capacitance of the load that that inverter presents, C. So every inverter is characterized by a K and a C. And given C, if you put a load on it, C load, the fan out on that device is going to be C load divided by C. So that allows you to calculate the timing of its output. So in this chain, all the devices can have, let me just simplify matters and make a K equals 4. All the devices have K equals 4. But they have different capacitances. This one has like 0.01 picofarads. This one may be 10 times as big. And this one 10 times as big again. And again. Now, how fast will this thing work? Well, in general, if you look at the formula for the delay at any one of these nodes, or the delay through a pair of these things to get rid of the difference between a rise and a fall time, those delays are all the same because the fan-outs are all the same. The ratio between this C and this one and this one and this one, they're all the same. So the total delay through this thing is like the number of stages times the fan-out. And you can throw in different factors depending on whether you're talking about rises or falls or pairs. But let's not look at that for the moment. Time delay is the number of stages times the fan-out times constant factors. You want to minimize this under the constraint that the total fan-out, that is the fan-out of each stage raised to the power of n, is equal to some total gain that you want. Call it gain total. Okay, given this constraint, you want to minimize this function. It's a fairly simple problem. Does anyone know what the answer is? So there's two parts to this answer. There's what's n and what's f. And there's a very simple answer if you pick the right part, and that is that minimum time delay implies that the fan-out is equal to E. And in that case, the number of stages is equal to the natural log of the total gain. And the time delay is equal to the fan-out of E times that, so it's proportional to n. Time delay is equal to E times n, times these other constant factors. Okay, so now we know how to optimize the speed of driving a big load. You use a number of stages, each with a fan-out of E, as many as it takes to get that much gain. Is that clear? Are there any questions on that? Dan?
Well, do you really want, I mean, in our simplified view, I'm wondering if you don't really want a little bit bigger fan out or something because there's really other things going on.
Yeah, that's an excellent question, which is often overlooked. That, in fact, I've only optimized one thing here, and that's time delay. And the important question to ask is, what other things might you want to optimize? And is there a good reason to be off of the optimum on time delay in order to optimize something else? And the answer is yes. In fact, we seldom operate with this low a fan out. The reason is it causes too many stages. Okay, so let's consider the case where we say arbitrarily, let's use half that many stages and a fan out of E squared. Okay, can you see what the change in the time delay will be? Let's just try that case over here. Let's say a fan out equals E squared, and the number of stages is going to be 1/2 of the log of the gain. The total delay is the product of these two numbers. That's n times f. So now the total delay is going to be same as it was before, has a factor of log gain in it. But now instead of being E times log gain, it's E squared over 2 times log gain. So you can see we've increased the time delay by a factor of E over 2. So we haven't quite doubled it. Okay? So that's sort of a reasonable point. It's fairly far off of the optimum. It only requires half as many stages of amplification. But it doesn't take you 100%, doesn't make your time delay 100% worse. So you typically don't want to go much higher than that number. Severa?
Why were you concerned about the number of stages there? Is it not true that you're getting this extra capacitance by making these guys on the right much bigger?
Right.
And doesn't the right
in my
hand
example,
dominate?
in my example, the fan out of each stage is 10, and there are 4 stages. If I wanted to do this with optimum time delay, I would have needed 8 stages, approximately, with a fan out of E, or about square root of 10.
But that's an area question that you're concerned about, right?
It's area, and it's there's some other things in here that are hard to estimate, like the time due to stray capacitance due to your layout.
Well, this wasn't the
and so
whole
on.
story then of minimizing.
To really minimize it, you have to hack the design and get the strays down too. This only takes into account the actual capacitance of the driver devices.
So it's not really as so in fact cutting it down is not really as bad as this right hand column. Is that right?
More than likely, it won't be as bad because saving space probably means saving stray capacitance. So you may have less. That's not obvious, but that may be true. Stu?
If you're trying to save area, it seems like an unbalanced approach might be better, where you cheat more on the fan out of the last stage so that you can make it smaller.
It's absolutely true, and that's typically done. You can gain a lot by, say, if your final load is 200 picofarads, and if I had this chain of devices with a fan out of 10 each stage, and this was driving 200 picofarads, then the last fan out would be a factor of 20, which is going to be way off the optimum, but only one stage is way off the optimum. And as a result of that stage being off, all the others get to be a lot smaller. So you save a lot if you sort of cheat on the last stage. However, that also introduces a lot of load dependence in the time delay. If you do just the opposite and you make the fan out of the last stage very low, then if someone comes along and doubles the load, it's still low and it doesn't change as much. So if you want to have delays that are not very dependent on the load, don't cheat on the last stage, but make its fan out low instead of high. If you want to save area, make its fan out high. I know there's too many complicating interactions here. Typical fan outs that we use are on the order of 4 to 10. Let me go through a quick example. I've prepared one here. Say on a chip you have a line that goes across 200 shift register cells and has to drive pass transistors, each of which is minimum size. So the total load is going to be 200 times the capacitance of a minimum size pass transistor. If you remember the capacitance at least in the parameters I passed out of a gate area is about 4 times 10 to the minus 4 picofarads per square micron. And if you multiply that by the area of a thing 6 microns on a side, that's 36 times 4 times 10 to the minus 4. If I look in my notes, I could probably find out what that comes out to. It's about 0.015. Which is equal to the incredible huge number of 3 picofarads. Okay, so how are we going to drive these 200 gates? Well, let's just pick some numbers. Let's use a super buffer because that'll be faster. Okay, so here's the load, 3 picofarads, and here's a super buffer, which may be inverting or non-inverting. Let's look at what it consists of. Essentially, the fan out of this device is going to be the ratio of this load to this capacitance. And the rise time of this node will be kf tau over 4. 4 because it's a super buffer instead of a regular inverter. And we'll use k equals 4, so that'll be f tau. Now if we use a super buffer for this stage, and regular inverters on previous stages, they have slower rise times. And that's another reason why we can cheat on the fan out of this last device compared to the previous ones. And in fact, let's give it a fairly high fan out. Let's pick f equals 20. Okay, with f equals 20, easy way to estimate the size of this driver device now, instead of looking at picofarads and working out what its capacitance is and working back to a size, just take the size of the devices we were driving here and divide it by 20. So there were 200 minimum gates there, divide that by 20. So this has the area of 10 minimum gates, which means it has a length of 1 and a width of 10. Okay, so that's an impedance of 1/10. Let's see, is that what I wanted? Well, my example says I picked a fan out of 10, and therefore I used 20 over here. So 10 is a more reasonable number for the fan out. So, and the other advantage of this choice is now I can divide 20 by 4 to get this device, which has a length of 1 and a width of 5. Integers are nice. All right, now this gate and this gate are both loads on previous devices. Let's just see how I did that. Assuming that we want to make the sort of slower form of this, which is where the last inverter drives the bigger load. Suppose this is the way we need to do it. Let's pick a fan out on this node that's lower than what we had out here, since that was a super buffer. And this gives this one a length of 1 and a width of 4. So in one step, we've gotten down to the point where the load on this input is 4 minimum loads in this inverter and 5 on that pull-up device. So now the capacitance on this node is equal to 9 minimum squares, if you will. And so if that's driven by a minimum inverter, that would be a fan out of 9. But if we drive it by something with a width of 2, then that's a fan out of 4.5. We can go through and calculate the delay of each stage now. You see, in each case, we used fan outs that are higher than the optimum, but not a whole lot higher. This one is higher than E squared, but since it's a super buffer, its delay won't be much longer than the other stages. Of course, a rough rule of optimization is make all the delays about the same. So that's sort of a sensible region. If you go through and calculate the rise time on this output, for tau equals 0.3 of a nanosecond, the rise time or the fall time is really just f tau. F is 10, so that's going to be 3 nanoseconds. That rise time or the fall time will be 3 nanoseconds. And if you look at this previous node, see how I did that. That node has a rise time of kf tau with a fan out f of 5, K of 4, so that's 20 tau. 20 times 0.3 is about 6 nanoseconds. So, in fact, this is sort of a reasonable design. Now, from here to the output, the load is going to be about 9 nanoseconds. And the advantage of using this super buffer here with sort of a moderate fan-out for a super buffer is that the rise time on this output node, since it's faster than typical internal rise times, means it's not very dependent on the actual number of loads. And if you build your clock drivers this way, then your clock skew won't be too dependent on how many loads each line drives. So it's best to have a super buffer at this point and keep the actual clock rise time fast, even though the internal delays may be longer, because you can build these the same on all your clock drivers. Then your skew won't be too dependent on the loads. Jeff?
Yeah, I'm choosing on whether it's an inverting or non-inverting super buffer. That is, which of the lower or upper is hooked to the last stage.
Yeah.
Don't you want to set that up so that you get your underlap versus overlap in the right way? Because if you've got overlap on the direction that you actually want to drive.
Yeah, okay, I hear what you're saying, that the way you choose this is going to affect clock overlap and so on.
No, the overlap between which of the two transistors is on. So you'll
Oh,
have,
you're worried about whether one of these turns on before the other turns off and so on. Yeah, I've not thought much about that problem. But usually the choice of inverting or non-inverting is determined by what you really need, what signals you have available and what signals you need to drive. You don't put an extra stage in just so you can choose the one you like.
that could affect your fan out.
It will affect your fan-out, sure, and that extra stage might not hurt you speed-wise.
The line which drives the upper transistor in the super buffer, do we have to calculate anything about it?
Yeah, you have to calculate the delay on this node too. And what I said here is that, yeah, in the fan-out, and that's why I said 9 squares here, because it's got 5 here and 4 in here. The limiting slope, the limiting edge is likely to be the output of this inverter, since it won't finish switching until this one finishes switching. So I just analyzed that case. And depending on how far back you take this, and where your signal really comes from, you can add more delays to see what your total clock driver delay is. You could add the delay on this node with a fan-out of 9, K equals 4, that's 36 tau, which is closer to 10 nanoseconds. So with these numbers, this isn't a particularly optimum clock driver. But if, in fact, this was the input, then it would be better.
Going back to your choice of width over length, in order to get the area ratios, I assume that it's to do with the current area capacity of the devices that you would choose for wider width to length as opposed to just area consideration.
Oh, yeah. If you just make the area of the devices bigger to get that capacitance, that doesn't help your gain. What you really need in order to get current gain and higher speeds is you really need a lower impedance, which means a larger width. It doesn't do any good to increase length and width. That gets you more capacitance without any more ability to drive a load.
So what's the limiting factor? I assume that when you choose a Z which is as low as possible, which
Well,
means you put it.
the Z's all interact, and that's the point. The Z from one stage to the next. Each one is chosen so that at each point the fan-out is reasonable. You don't want to have any stage where you go from a small Z to a very large Z, because it'll be very slow. It's better to use several stages where the Z's only change by small factors. And that's what all that's about. Joe?
How many of these decisions do you have to make fresh with every new design, and how many do you sort of steal from old circuits that you designed and work for?
Yeah, it's quite plausible to make a set of drivers like this and use them throughout a circuit. And then the next time you go to do a project, you may find that you have only half as many clocks to drive as you had before, in which case the same devices will work. The output nodes will work faster, and they won't be quite optimum, but they'll still be adequate, as good as they were before. And if you have more clocks to drive, you may find your old design won't quite cut it and you have to change it. But you shouldn't have to redesign it every time you do something different, unless you need to fit it into a different arrangement of lines or something. Well?
Is there some sort of limit on the
how small you can make the length compared to the width? I mean, you're down at 1, and that's kind
Yeah.
of small.
The length of a transistor in any device that's trying to drive a load is going to be 1. The length of a transistor is the most important performance determining dimension of the technology. There's no reason to use a length more than 1 unless you're trying to make a low power device that needs a long skinny pull-up. So pull-ups, which are high resistance devices, are the only place you'll ever see a length greater than 1. Okay? Okay, one other subject is I/O through pads. How do you drive the outside world? Well, it's the same type of circuit, but I want to give you just some ideas about the layout of that. You typically find that the pads that you bond wires to are large compared to anything else. When you go to drive the outside world, you typically have a pad that's big enough to smash a wire onto. Okay, a wire comes in here and gets smashed in a blob there, flattened out some. This wire usually it forms a blob that almost covers the pad, and the size of that pad is like 100 microns. For those who think English, that's about 4 mils. And the diameter of this wire is about 1 mil, 25 microns. Keep in mind that that's about 4 times as wide as the length of a typical transistor. But to drive this 50 picofarads out here, remember in the previous case we had 3 picofarads to drive and we used a width of 10. So now to drive these 50 picofarads we need a width of 100 or so. So the gate of that transistor has to be about 100 squares or 600 microns long. This is only 100 microns. So where are you going to put that device? Well, one place you can put it is put the gate like this and put the green region all around it. And now put, for example, ground out here and hook this one to the pad. So when you drive this red line high, it connects the pad to ground through this extremely wide transistor. Current flows across this thing in all directions. This is one typical way of making an output driver. And the other way to make that is take this red gate and run it in a sort of snake configuration and with green all around it. But in any case, you have a long skinny red line, which means a short fat transistor. And some of the pads I've designed actually have 2 red lines wrapped around them with power on one side and ground on the other and the pad connected in between them. Dan?
I'm not clear. Does the green go all the way up to and under the pad?
The green could go under the pad. It has to be connected to it. In fact, I think we would typically not put the green under the pad, but bring a blue line out here and sort of put contacts all over here. So.
I understand the green being grounded.
Well, this is to indicate that this is a pull-down device. It is. It pulls this output wired to ground. And there'd be another device, something like it, that pulls this output wired to high. And for TTL compatibility, what you can do is on the pull-up device, instead of using a depletion mode transistor in a super buffer, go ahead and use an enhancement mode transistor, and it won't pull quite all the way up to 5 volts. And your TTL may be happier to see it only go up to 3.5 volts. Although it probably won't mind if you use a depletion device there either. Other questions? Marcelo?
Yeah, a trick that is commonly used is some low-power Schottky devices allow inputs up to 12 volts without crapping out. So, common practice is if you and some people even get some of the manufacturers to sell them spec TTL devices that go to high voltage. I have another question. Is there any protection for inputs, like if you're walking on the rug and you happen to come up and...
Yeah, I mentioned lightning arresters yesterday, but I didn't say much about them. On input devices, If you make this a tri-state device, let me show you how you do that. Work around to that question. If you connect NOR gates on both of these, if this device is that device, okay, and that's like a length of 1 and a width of 100 squares. If you hook a NOR gate here, this is no longer exactly the same super buffer, because if you put a 1 in here, both of these guys get pulled low, and this is no longer being driven in a complementary fashion. And if this is an enhancement mode device, it will in fact shut off. So let's make that an enhancement mode device. Now you can make a tri-state device this way. And this is both an input and an output. You could take this as an input to your circuit, and your output will be driving these guys, and that will be enable bar. So when this goes high, it disables. If you make a device this way, when you're using it as input, both of these devices are shut off. If you apply accidentally a charged up finger to this pin and you put a whole bunch of voltage on there, you don't want that voltage to get into your circuit and start blowing out your gate oxide. So what you typically do is put a little bit of series resistance in here. And with that little bit of series resistance to limit the current, and with these devices hanging on here with these extremely wide channel regions, these devices will exhibit an effect called punch-through, where they really can't support enough voltage to damage the rest of your circuit. And so they will in fact sink that static discharge current through both of them into your power supplies. And that'll protect your circuit. If you have strictly an input device, an input pad doesn't have all this junk hanging on it, then what you can do, simply hang a transistor on it and turn it off. Okay? This device is always off, except it's got this special feature called punch-through, where if the input voltage rises too high, this thing will shunt that current to ground before it gets high enough to blow out the rest of your circuit. And that's a non-destructive conduction, whereas blowing out a gate oxide over here would be destructive and it would never work again. So this punch-through prevents that breakdown. Stu?
What kind of trouble would you get into if you try to use that circuit plus the standard output circuit so that the resistance of the input protection didn't affect the DC level of the produced on the output pin due to the DC current of the TTL you're trying to drive?
Well, yeah, if you make this resistance very low so you don't have to worry about what it does to your load, then these transistors have to be effectively wider to sink the extra current you get when you hit that thing with a bunch of charge.
Is there a rule of thumb as to how much current you can run through?
I don't really know what the rules are, and I have no way of estimating how much current you get from a discharge when you touch the thing. But there are some rules that say that these devices should be on the order of 100 squares.
Okay. Is the general rule of thumb, the punch-through resistance of a channel, the same as the turned-on resistance?
I don't think so. If you look at the curves, if you look at the family of curves for a transistor with drain current versus voltage drain to source, every one of these curves at some point takes a leap this way, and the amount of current you get through there becomes pretty much independent of which curve you're on. It doesn't matter what the gate voltage is too much. At some point, they're all going to punch through. And I'm not exactly sure what that dependence is. Okay.
How do you implement the series resistance?
This series resistance is usually a small number, something on the scale of things of the outside world, like 100 ohms, and therefore it's some number of squares of a green line. For 1,000 ohms, you'd use 100 squares of diffusion line at 10 ohms per square.
So can we get a sample? Is it on file? Do you have any sample info?
Yeah, this is a standard device that's made up, and in fact, it's in a file called pads.ic for those of you that picked up a disk from us. It's also to be found on the Icarus directory on Ivy. Okay, let's look at one other question concerning pads. got this output pad with this huge driver transistor on it. This huge red line. And somewhere over here is the rest of your circuit. And you have an output. You want to send that output out through that pad. If you just hook it up directly, you've got an awful lot of load to drive here, and it's going to be pretty slow. So you know you have to put some gain in there somewhere. So the symbol we use for, the cell we use for driving the outside world has, in fact, some big amplifiers in it, sort of medium size with fan-outs on the order of 4 and 8. But the thing I want to point out now is that the limiting speed on getting your signal out through this device is probably going to be the delay caused by this little device here driving this wire. And then, in fact, to improve it, you probably want to put some amplification here at the front end of a long run. Whenever you need some gain, it's best to put it before the long wire rather than after. Okay? Okay, let's go on to something completely different. There's one other concept I want to talk about how you can get off a chip in a hurry. That is to say, how you can get off a chip fast if you're not in a hurry. And that is, use clocked buffers. Use a shift register where each stage of the shift register is bigger than the previous one. Okay? If you look again at optimizing the delay through this structure, the delay is going to be some number of clock cycles, not just some number of prop delay nanoseconds. And if you don't really care about whole clock cycles, but you just want to be able to stream data through this thing in a hurry, then the optimum ratio to use on these things is the ratio that gives you the smallest possible fan-out. That is, each one should be just a tiny bit bigger than the one before it. So there is no optimum. The optimum is 1 plus epsilon. But if you can't afford an infinite amount of area to get your gain up in an infinite number of stages. So if you optimize something else like speed times area, you can come up with a reasonable fan-out on the order of 2 or 4, depending on what function you optimize. So the point is you can get data off a chip a lot quicker if you clock it between your amplifiers. Okay, Dan?
Well, I was thinking that if other considerations determine your clocking, like that you get 8 gate delays per clock cycle, that you'd be inclined to raise your gain up so that the thing just got done in 1 clock cycle, so you get the biggest
right.
data.
If you've fixed your clock cycle and you know there's a constraining critical path in here somewhere, then you make the gain of this enough that it roughly matches that critical path. Then you don't need many stages. Okay, so if you really want to stream data off your chip fast and you don't mind a few cycles of delay, consider building a clocked buffer. Anything else?
I don't get what you mean by fast. I mean, you'd have to, the only way I can see it being fast is if you had to do that delay, that shift register anyway. Many clock cycles is a lot slower than
pipelining.
It's pipelining, right. It's getting a bit per clock cycle where you can clock it much faster than you could if you had the large fan-outs. So what this buys you is the ability to clock faster.
The delay you showed us on the thing before was longer than 1 clock cycle typically.
If it was longer than 1 clock cycle, then you can't get a new bit out every clock cycle.
But that's typically true, right?
No.
No, you slow the clock down.
Okay.
You slow the clock down usually until you can get data out on every cycle in most systems. In this one, there are times where you don't need data out on every cycle, of course, and you can afford the long delays. And in fact, as the technology scales and on-chip things get faster and faster, and the gain between on-chip and off-chip gets more and more out of hand, you will tend to design things which have a fast internal clock and a slow external transfer rate, unless you do this trick to stream things off the chip quickly. Okay? Okay. In the remaining 30 minutes, I want to tell you about a project that I'm working on and a chip that I designed. And I'll need the view graph projector here. This picture is just to introduce my project, which is essentially speech processing. This is a spectrogram of some words. This is a plot of time in the horizontal direction, 30 different filter frequency channels in the vertical direction, and each black bar corresponds to the logarithm of the power coming out of that filter channel. This is the kind of thing I want to build. And this is sort of the project that motivates the chip I'll be talking about. And there are plenty of other examples of speech processing that are of interest. And I brought along a toy that Texas Instruments made, which is a speak and spell, which just sort of illustrates the concept. If you punch the on button, it beeps at you. And if you punch something like a letter, it says the letter. I just punch D, and it says D. And that sets the level of difficulty for spelling, and it'll ask you to spell words. For example,
spell lettuce.
So it asks you to spell lettuce.
Lettuce. That is correct. Now spell feather.
That incredibly functional box, which plays about 3 or 4 different games and has speech synthesis by digital filtering in it, has only 4 chips. 2 of those chips are read-only memories. And one of those chips is a microprocessor. And that leaves 1 chip that knows how to talk. Okay? Well, I want to make a chip that knows how to listen. And it's got to be easy. It's only about 1 order of magnitude more complicated. And 1 order of magnitude be ready for me to build it before I get it designed. So let's plunge ahead. Doug ran off, so I have to change my own slides. Sure. Okay, this next slide is a picture of sort of the architecture that is useful for digital filtering. And what it shows is basically a bunch of junk interconnected in the form of one of the things I wanted to build. But it illustrates the fact that there's only a few basic elements that I have to design. There's an adder. I intend to use serial arithmetic throughout this system so that an adder is something with the complexity of a few gates. That's no big deal. I want a multiplier that I can stream operands through as fast as I send them through an adder. And therefore, it has a complexity of like n adders for n-bit words. So the multiplier is an order of magnitude or so more complicated than an adder, bigger in area. And then it's got this box labeled z to the minus 1. That's an operator used in digital filter notation, which means 1 sample time of delay. Whatever goes in now comes out later. And a sample time in this case is a sample time of the audio signals we're talking about, which is at 10 kilohertz sample rate, that would be 1/10 of a millisecond. 1/10 of a millisecond is a long time in this kind of technology. So if you think about running serial numbers through there, that gives you, for 20-bit numbers, that gives you still a long time for each bit. So what you can do with that element is run that whole box multiplexed over a whole bunch of different filtering operations. And in fact, that delay becomes any number of words of delay as long as every word comes out 1/10 of a millisecond later than it went in. So in fact, what I'm building there is a 32-channel filter, and that box labeled z to the minus 1 is like a long shift register that delays 32 words 24 bits long, which means in total it's about, what is that number, 700 and some odd bits. Okay? So that's a long shift register. Now, if you think about building shift registers the way we've been talking about, you begin to see what the problem is. If you have 700 and some odd clocks to drive, you got lots of clock driving buffers, that's okay, you could cope with that. But if you have 700 and some odd pull-up devices sinking a lot of power and you cram them into a very small area, that chip is going to be a real, pretty good effective space heater. So the problem is very simply stated. The problem I'm discussing now is simply the design of this shift register. How do you design this box 700 bits of shift register to have all the good properties that everyone wants in their circuits. That is, it has to be very small because, as you can see, I need 3 or 4 of them on the chip. It has to be low power because with that many on a chip, that chip's going to burn up otherwise. And it has to be fast because I want to run as many channels and as many bits per word through there as I can. So fast, low power, and small, that's all I want. So. Now here's what I had to work with. These are the process parameters. These are not exactly an old version of the numbers that Doug told you about. These are not taken from the NSIL 1 process that Xerox has, but these are taken as characteristic of typical lambda equals 3 micron processes. For example, the one that we actually had this fabricated on at Morimon Integrated Circuits. You can just look at those for reference later if you wonder how I came up with some of my numbers. Let's go on to the next one. This is an interesting device that I found useful. It's called a, this is an idea of how to make a RAM out of a 3-transistor RAM cell. Let me just show you what the concept is that I want to work with here. I tried a lot of different approaches to making this long delay, including thinking about charge-coupled device delay lines and so on, which turns out to be probably the smallest area and lowest power approach, but involves technology that I wasn't willing to take the time to learn and understand, and sort of analogish in nature, and would take probably a lot of grief to make it work. So I decided to do this all digitally. I didn't want to get into sense amplifiers because I'm afraid of analog stuff on a chip where I can't play with it. So I want to do everything digitally. And that led me eventually to the concept of a serial, parallel, serial architecture, which many of you are probably familiar with. What I need is end-to-end a serial bit stream, and I'll just run it into a shift register here. And then I'll use that as a serial to parallel conversion and write words in parallel into a RAM. And then later, 1/10 of a millisecond later, when I need that word back, I'll read it out into another shift register and send it on its way. So this is called a serial parallel serial organization. And this has the advantage that, unlike a shift register where every bit moves on every clock cycle, in this example, only the bits here and here move on every clock cycle, and they sort of sit still in the middle of this RAM in between times. And this RAM doesn't have to be particularly fast because it's got, if these are 24 bits long, it's got 24 complete clock cycles in order to do this read and a write operation. So its basic cycle time would be, say, 12 clock cycles to do a read or a write. So there's no particularly stringent speed requirements on this RAM if parallel means wide enough. Okay, so let's look at the kind of structure I decided to use to implement that RAM. It's called a 3-transistor RAM cell. It's a dynamic RAM. I'll show you here. Start with the storage node. Every storage device you make, dynamic RAM or shift register, is based around some storage node where you leave charge. You isolate that by cutting off this transistor. And you put new data in it by turning on this transistor. So to write this device, we'll put a 1 on this write line, which means write this column. Think of a whole stack of these guys in here sharing that line. They all get written at once. But in particular, this one gets written. When this line goes high, whatever voltage is on this bit line gets transferred into this storage node. So that's how you write it. Assuming, of course, that somehow you put something on the bit line first. And then later, when you want to read out of this device, if you enable this, if you pull up on this read line, it turns this transistor on, which connects this device to the bit line. Well, connecting it to the bit line doesn't mean that you've read out its state. What you have to do is pre-charge the bit line to a high state. Then when you connect it, if there's charge stored on this gate, this will be turned on, and it will pull down on the bit line. Now, if you're particularly interested in the details of this, you can go through this timing diagram, which shows a cycle of pre-charging the bit line writing something into the cell, pre-charging the bit line again, and then reading it back out of the cell. In actual operation, we don't read it back out until a long time later, but in this example you can see that if you put the data in through this device, which looks almost like the same device you used to read the RAM, you use this device to write it. When you enable a write, you let the data in pull down on the bit line after it's been pre-charged. If you look through that timing diagram, you can see approximate waveforms for both storing and reading a 1 and storing and reading a 0. Okay, let's go on to the next one. Next picture is a color layout of that. The copy I handed out is not an exact copy of this, but it's got a little more annotations on it. If you recall, each cell needs a ground connection, it needs a connection to a bit line, it needs a connection to a vertical column write line and a vertical column read line. And so for this device, I picked the colors for those as blue metal bit lines and blue metal ground lines, which are shared between cells. All the lines have to be distinct except ground. Ground is the same everywhere, so that's the only line I got to share.